Right. Thank you, Chair, for the introduction. I'm Mohammed, and today I'm going to present SoftVN, our proposal for efficient protection for off-chip memory in today's processors. This work was done in collaboration with Weizhe, Professor Zhang, and Professor Edwards at Cornell University. All right. So in this work, we target trusted execution environments, or TEs, in today's processors. TEs are secure hardware compartments that provide strong protection for confidentiality and integrity of code and data of programs, even from low-level software and physical tampering in the external DRAM. TEs are otherwise known as enclaves or secure processors. And examples of TE include Intel SGX, AMD SCV, ARM Trustzone, and BRICS5 Keystone. A key technology to enable TEs is that of the off-chip memory protection in today's TEs. For any data leaving the trusted CPU chip and going into the untrusted DRAM, its confidentiality must be maintained by using encryption. Moreover, its integrity must also be maintained or verified by checking on a memory read that it returns the most recent value that was written by the processor at that address. However, this mechanism of off-chip protection is the main source of overhead in today's TEs, especially for memory-intensive applications. On the diagram on the left, we can see the normalized execution time of various applications when they are run inside a CPU TE simulator that we built. These applications are from different domains such as neural networks, graphs, and bioinformatics. We can see the performance overhead inside a TE is very large. It can be as high as 80% for some applications. This is because TEs require additional metadata to be stored alongside each cache block in the external memory, and also to be fetched on each memory access. The key takeaway here is that the external metadata can incur a very high bandwidth overhead, as much as 200% for some applications. So in SoftVN, we propose to reduce the overhead of off-chip memory protection by tracking the external metadata in software. This is the result of our observation that many data-intensive applications have simple write patterns to their data buffers. What we observed was that they have simple write patterns in which they update all the elements in their data structure the same number of times, sequentially. So the key idea here is that the version numbers, which is one kind of metadata which we focus on this paper, that reflects intuitively the number of writes to a memory block. And in traditional protection, the baseline, the version numbers are per each memory block. Whereas in SoftVN, our proposal, we propose that the version numbers, there's one version number for many blocks in a big data buffer. And that version number is tracked by software and provided by software for memory reads, thereby reducing the decryption latency and hence lowering the performance overhead. So before we understand SoftVN, let's look in detail at today's off-chip memory protection. So any data that is leaving the trusted CPU chip boundary must be stored in encrypted form in external memory. For that, we use standard AES engines for encryption, which will take in a counter value and transform it into a one-time pad that will be XORed with the plaintext with the encrypted data. The counter value consists of the physical address of a block and a per block version number that reflects the number of writes of the memory block to off-chip memory. And because the VNs are per memory block, they are very large in number themselves. They cannot all be stored on chip, so they must be stored in external memory and fetch back when the data itself is fetched back for decryption. Moreover, for the integrity of the data, we also need to store MACs, which are message authentication codes, and they're calculated using cryptographic hash functions. And they are also fetched back when the data is fetched back for decryption. In addition, to prevent against these so-called replay attacks, we need to create an integrity tree of MACs over the version numbers, so that even though an adversary might replace this external data with some stale value, we can detect that by traversing the tree whose root is on chip, so we can detect any tampering in the external DRAM. This whole mechanism incurs a high performance overhead in today's Ts, especially for memory intensive applications, because their memory footprint is larger and the metadata is also proportionately larger and the tree is deeper. So we need to traverse the deeper tree and hence fetch much more metadata on each memory reach, which incurs high performance overhead. So in SoftVN, we propose to reduce that overhead by tracking the version number in software. So basically our intuition is that once we studied many data intensive kernels, we found that they have simple write patterns. So, for example, consider DNN inference here. It has a number of kernels and they write to data buffers such as output feature maps. And what we found was that these kernels update all elements in this output feature map the same number of times. As such, we can have one version number per entire data structure instead of per cache block. In this example, if we assume that each kernel will write to all elements one, we can intuitively have the VN increment by just one after each kernel, and we can track the VN increments in software. So based on our intuition, we propose SoftVN as an extension to current memory protection schemes by having a new region in the memory, which stores data buffers which have simple write patterns. And the idea is that software will provide the VNs for data in this region when it is decrypted. Let's see how that works. In traditional protection, the software, when the memory request is generated, the encrypted data back that returns from the DRAM also has to fetch the VNs to perform the decryption. And eventually the decrypted data is sent back to the caches and the core. However, with software provided version numbers, the idea is that when a memory request is generated, the VN is attached to the memory request. And for decryption, the response will use the software provided VNs to do the decryption, not rely on the external VNs. However, even though software provides the VNs for memory decryption, we still have to store them in off-chip memory because processors are complex. They have many mechanisms like cache block writebacks, paging, prefetching, which happen independent of the software. So this mechanism still requires the off-chip VNs, and we propose to update them in the background. So while realizing SoftVN in hardware, we face a number of challenges, which I will explain using this simple example of a vector-vector addition kernel. In this example, we assume that these data buffers have simple write patterns, and they are stored in the SoftVN region in DRAM. The first challenge we faced was that how to have the software provide the VNs for the memory access efficiently. Naively doing that would incur a high instruction overhead because we would do that for each memory access, and this would lead to this instruction paste inside the loop. We need to do this more efficiently. So for this, we propose a hardware VN table, which stores VNs for different address ranges, that is for different buffers. And SoftVN proposes new hardware instructions that will allow us to set these VN table entries for different data buffers. SoftVN also provides a new instruction to clear up the VN table when it's no longer needed, for example, at the end of a kernel. And the VN table has a fixed number of entries like 16, and it's searched through on a memory read to any of these buffers. So with the VN table, the modifications to the kernel will look like this. There will be instruction at the beginning and end of the kernel, but nothing inside the loop. It's more efficient. Let's see how the VN table is used when we load an element of the data buffer X. So firstly, we assume that there are range registers, memory range boundary register inside the processor that will search detect if there's an access to the SoftVN region and trigger the appropriate SoftVN related mechanisms. So while there that the hardware will search not from the off-chip VNs. The second challenge we faced was that instruction. They usually access a word at a time. For example, a 4-byte word. whereas off-chip accesses happen at a cache line granularity. Hence, VNs are also for a cache line granularity. So if you look at a single cache line, there are a number of words or elements inside the cache line. And while our simple kernels with simple write patterns are updating the cache line, it is entirely possible that the cache line will be unpredictably evicted and to the DRAM, and that will cause an increment in the version number for this block. Whereas the whole idea of our proposal is that we are tracking version number in software. So we cannot allow the cache line to be evicted unpredictably. For this, we need to collect all the writes in a cache line before we allow it to be evicted. And for that, we propose a secured memory buffer, SMB in the processor core, which is like a small cache. And it stores a single cache line for different data buffers. SoftVN provides a third instruction map, which links an entry of the VN table to the SMB. In this case, that would be Z, because Z is the only buffer that's being modified in this kernel. And SMB will store a cache line for Z at a time. And Z will point to its VN table entry so it can load the VN later. SMB has minimal number of entries like 4, because in a kernel will only modify so many data buffers at a time. So let's see how a load to the SMB works. It's actually quite similar to that of X. The load for Z would fetch its VN from the VN table. It will attach it to the memory request and send it to the hierarchy. The response will use the VN in the memory request to do the decryption. However, because Z is being modified, its VN also needs to be updated. So in the background, we will fetch the VN from DRAM so that it can be updated later. As I mentioned, the SMB has only stores one cache line at a time, whereas Z obviously has a number of cache lines. But because Z has a sequential write pattern, we can have the hardware automatically load the next cache line of Z each time the software sequentially make access to a new cache line of Z. And the previous cache line will be released by SMB into the L1 cache once it's done writing to it. At the same time as this is being done, because Z has been updated, the previous cache line has been updated, its VN needs to be incremented. So the hardware will get the VN of the previous cache line from the table. It will increment it by 1 and release it to the metadata cache. This is how VN increments happen in SoftVN. Whereas in traditional protection, the increments happen on a write back to DRAM. So in order to use the new hardware structures with SoftVN, we'll need to add instruction at the beginning and end of the kernels, and the original code will remain intact. The third challenge, which I will briefly describe, involves around the virtual to physical address mapping, which is controlled by the OS in today's Ts. And paging by the OS will cause a memory block to be relocated to a different location, which will obviously cause the VN to be changed. Whereas again, we are tracking the VN in software. So we cannot allow the VNs to be changed independently of the software. So to avoid this, we propose to use virtual address in the encryption mechanism. There are two types of operations to the DRAM, reads and writebacks. For reads, we can just attach the VA to the memory request, just like we did with the VNs, and the virtual address will be used in the decryption mechanism, just as the VNs were used. Moreover, to avoid cryptographic leakage, we have to use a new key for each enclave, because VS can repeat across different enclaves. For the other operation from DRAM writebacks, we have to use the VS have to come from some other place, because the software may not be running at the time of the writeback. So in this case, the VA will come from an already existent structure inside STX, which is the EPCM, enclave page cache map, and it already stores the VA for each page due for STX mechanisms, and it's convenient to get the VA from here. The VNs for the writeback can come from the metadata caches. So now that we have an idea of how SoftVN works, let's take a look at how we evaluated it. We studied applications and their kernels from different domains like neural networks, graphs, and bioinformatics. And generally, we found that the number of lines of code or the modifications we have to make to the kernels are simple, and they require minimal number of lines of code to be added. Also, the hardware number of entries they needed in the hardware structure are well within the limits we imposed on the hardware. which was 16 for VN table and 4 for assembly. For our evaluation, we used the ZSIM CPU simulator and the RAMulator DRAM simulator, and we augmented them with a memory protection simulator. For a baseline, we chose an Intel SGX-like protection. We modeled 16 gigabytes each for traditional protection and the SoftVN regions. And our kernels were written in C++ with new instructions added for SoftVN. So let's look at how SoftVN performs. On the diagram on the right, we can see the normalized execution time for various applications we studied. The BP or baseline protection overhead, which is the Intel SGX overhead, can be quite high, as much as 80%, and is 35% on average. Whereas SoftVN consistently deliver a low overhead, 5%. This translates to a 33% performance improvement and an 82% overhead reduction. Moreover, SoftVN reduces the external VN metadata traffic by 66%, and this is made possible by completely skipping the VN accesses for memory buffers, which are purely read-only. For example, in DNNs, there are model parameters, and in inference, we don't need to update their VN, so we'll completely skip their accesses. Thus, in summary, SoftVN greatly lowers the overhead for today's memory protection by allowing software to track the version numbers for large data buffers and providing them for memory reads. If you are interested, you can find more details in the paper regarding the hardware mechanisms, the applications, the security analysis of SoftVN, also some more results, including the sensitivity analysis. That's all for my talk. Thank you. I'll be happy to take any questions.
Unbounded computations with data. And the talk is going to be given by Umar Samardzic, the third-year graduate student at MIT. She said we work on accelerated cryptographic applications on the processes.
So you see this, you hear me? Thank you, Dimitrios, for introducing me and making a good effort to pronounce my name. So, hello everybody, my name is Nikola Samardzic, and it's my great pleasure to introduce CraterLake, a hardware accelerator for efficient, unbounded computation on encrypted data. I was very fortunate to do this work together with Axel Feldmann, Aleksandar, Nathan Manohar, Genise, Professor Srinivas, Karim Eldefrawy, Professor Peikert, and my advisor, Professor Sanchez. So CraterLake is a hardware accelerator for fully homomorphic encryption, or FHE. FHE is a cryptographic technique that enables computation on encrypted data. This means we can use FHE to, for example, securely offload computation to the cloud. But nothing good comes for free. FHE is 10,000 to 100,000x slower in software compared to running the same computation on unencrypted data. The computational primitives of FHE do not map out to existing architectures like GPUs because these primitives have complicated all-to-all dependencies between their elements. And prior FHE accelerators are only effective on a limited set of small FHE programs, like 3 to 6 layer neural networks, but they falter on larger programs like deep neural networks. CraterLake is the first FHE accelerator that is effective on programs of any size. Specifically, it supports a 5000x speedup over a 32-core CPU and an 11x speedup over state-of-the-art FHE accelerators. Now, to run Resident 20 inference on encrypted data today on a CPU takes over 20 minutes. And CraterLake brings this down to 250 milliseconds. Okay. So FHE plaintext are very large vectors with up to tens of thousands of real numbers. This plaintext vector can be encrypted into an FHE ciphertext that's composed of two high-degree polynomials with large coefficients. So for example, a 64K degree polynomial with 1600 bit coefficients. This implies a 25 megabyte ciphertext for a sense of scale. It's important to note that CraterLake does not accelerate this encryption process, but actually accelerates computation on the already encrypted ciphertext. So let's see what these operations are. FHE supports three operations of the underlying encrypted vectors. These are element-wise multiplies, element-wise adds, and cyclic vector rotates. But implementing something like an FHE multiply isn't as simple as just multiplying the corresponding polynomials of the ciphertext. You actually have to do many primitive polynomial operations to implement FHE, these three FHE operations. Specifically, we need to support four primitive polynomial operations, and these are element-wise adds and multiplies, and two more complicated operations that have wall-to-wall dependencies between their elements. These are automorphisms, which are structured permutations of coefficients of these polynomials, and number theoretic transforms or NTTs, which are used to speed up polynomial multiplication. So this diagram here shows the primitive polynomial operations you need to apply to implement a multiplication of ciphertext X and Y. The key switching algorithm is an FHE algorithm composed of hundreds to thousands of primitive polynomial operations. This makes it a key computational kernel in FHE because it's responsible for over 90% of compute in most FHE benchmarks. And we'll come back to key switching throughout this talk. So let's now dive into the details of why supporting large FHE programs is particularly challenging. The bottom line is that to support large FHE programs effectively, we need to work with ciphertexts that are up to 10x larger than what prior work effectively supports. Let's see why. So ciphertexts start out with a small amount of cryptographic noise that ensures the security of the underlying encrypted data. But as we apply operations on these ciphertexts, this noise compounds and must be trimmed. The consequence of this trimming is that the ciphertext size actually shrinks during computation, as shown in this plot. Smaller ciphertexts sound great until we realize that the ciphertext can only be so small before they become undecryptable. So this looks like we can only support programs that are of a limited depth in FHE. Well, fortunately, bootstrapping is an FHE algorithm that enables us to refresh the ciphertext back to a larger size, enabling more useful computation. This means FHE can support arbitrarily deep programs by simply separating them into subprograms of limited depth and bootstrapping between these subprograms. But being able to bootstrap requires working with very large ciphertexts, 25 megabytes, which means that, and prior work does not support these ciphertexts well. So that means prior work is limited to FHE programs of shallow depth, shallow enough to not require bootstrapping, basically, right? By supporting sufficiently large ciphertexts, CraterLake is able to accelerate arbitrarily large FHE programs, right? But targeting these large ciphertexts requires new architectural and algorithmic techniques. So let's dive into the architecture first. So both prior work and CraterLake use the residue number system, or RNS, to accelerate modular arithmetic of very large integers. So specifically, RNS leverages the Chinese remainder theorem to represent a very large integer, say a 1600-bit integer, as many smaller integers, say 28 bits each, and these are called residues. The magic of RNS is that we can implement a very expensive 1600-bit integer multiply as a simple element-wise multiply of all of the residues, much cheaper. Addition works the same way. And this same trick can be actually applied to polynomials. So if we have a very large coefficient polynomial, we can decompose it into many residue polynomials with much narrower coefficients. And polynomial multiplication can be done in a similar way. We just multiply the corresponding residue polynomial. Okay, so let's look now at F1, the state-of-the-art FHE accelerator, and how it implements an entity of a large polynomial. And we will see why it doesn't scale to large ciphertext required for deep FHE programs. So remember, I mentioned large polynomials are represented in FHE accelerators as many residue polynomials. So to apply the entity to the large polynomial, we simply have to apply it to all of its residue polynomials. Each one of these residue polynomials has tens of thousands of elements. So something like a vector processor architecture seems like a natural fit, right? Well, unfortunately, entities and automorphisms have complicated all-to-all dependencies between these polynomial elements, making a vector processor less than an ideal fit for this problem. So instead, F1, not CraterLake, F1 implements a multiprocessor with many identical compute clusters optimized for residue polynomial arithmetic. A network connects all of these clusters together, and what F1 does is schedules entire residue polynomial operations on a single cluster. So we can schedule an entity within one cluster, and the advantage of this is that the dependencies between of the entity can be resolved locally within a single compute cluster, right? To achieve good performance, F1 schedules many polynomial operations across its clusters in parallel. So this approach works really well for entities and automorphisms. But as you've seen, this animation showed many residue polynomials changing places. And that happens when you do key switching, which again is FHE's key computational term. And this is because the number of dependencies between residue polynomials actually grows quadratically with ciphertext size. All residue polynomials of the output depend on all residue polynomials of the input. Since dependencies grow quadratically, network traffic does too. Now remember, to support deep FHE programs, we need to be able to support large ciphertext effectively. But this quadratic scaling makes F1's architecture particularly poorly suited for large ciphertext, right? On top of this, F1 implements a flexible all-to-all network that eases scheduling, but comes at a high area and power cost. And despite the flexible network, scheduling for F1 is still a complicated problem and actually leads to poor utilization in practice. Okay, so what does CraterLake do differently? Well, actually, it does exactly what I told you in the last slide is a bad idea. It is a very wide vector uniprocessor architecture, right? So 2048 lanes, and the entire chip operates on a single residue polynomial. So we can see here how an entity is applied 2,000 elements at a time to only a single residue polynomial. And the entire chip is kept busy with this one operation because, as I mentioned, each residue polynomial has tens of thousands of elements. CraterLake also supports a 256 megabyte register file, which is necessary to achieve good reuse of FHE's large operands. Okay, but how is this actually implemented, right? The physical organization is 8 lane groups, and each lane group is responsible for its fair share of the polynomial coefficient for elements. So the lane group 0 stores coefficients 0 to 256 of all the residue polynomials. The lane group 1 stores coefficients 256 to 512 of all residue polynomials, etc. So the advantage of this is that all of a sudden dependencies between residue polynomials can be resolved locally within lane groups. But of course, the drawback of this is that now entities and automorphisms which have dependencies between coefficients have to require global communication through an on-chip network. And remember, F1 doesn't have this global communication problem for entities and automorphisms. So why is CraterLake's approach bad? Well, first of all, our idea to resolve dependencies between residue polynomials locally and dependencies across coefficients of the same residue polynomial globally is a worthwhile trade-off. This is because now communication through the network grows only linearly with ciphertext size and not quadratically like for F1. And the second very important part of this story is that we can implement these dependencies between entities and automorphisms using a fixed network that requires no control logic. So let's see why that's the case. Again, entities and automorphisms are the ones causing us trouble here with dependencies between lane groups. But we can resolve all these dependencies using a fixed function transpose of the coefficients of the residue polynomials. So that's the insight that really enables this very wide uniprocessor architecture. And again, this permutation the network has to apply is fixed. It requires no control logic and implemented by just wires. And this example shows the specific permutation you have to apply for a toy example of a 4-lane group, 4 lanes per group version of CraterLake. And so the advantages of this approach are a 16x smaller area for the on-chip network compared to what CraterLake, compared to what F1 would require to achieve the same performance. Okay, so those are the architectural contributions, but there's also algorithmic problems, right? Specifically with respect to key switching, FHE's key kernel. So prior accelerators target standard key switching, but boosted key switching, a different newer FHE algorithm, scales much better than standard key switching, both in terms of compute, but most importantly, footprint. So you can see here, standard key switching can have a footprint of up to 1.7 gigabytes, while boosted key switching only has a footprint of up to 52.5 megabytes. So it's really necessary for large ciphertext to be able to do boosted key switching well. Now, prior accelerators, as I mentioned, are focused on standard key switching, and the bulk of operations in standard key switching is actually concentrated in NTTs, which have each NTT has an order of magnitude more compute than the simple multiplies and adds in the breakdown of this table. So most operations are in NTTs. Prior work supports NTTs well, and so it can do standard key switching well. But boosted key switching has most of its operations in the simple multiply and add operations, and much less in NTTs. So the problem with this is that a naive implementation of boosted key switching that goes through the register file would actually bottleneck on the register file bandwidth or number of ports. So we designed the change RNS space unit, or CRB, to encapsulate most of these multiply adds, and this allows us to have much higher throughput than if we went through the register file for each operation. The CRB is designed as many parallel multiply accumulate pipelines. So this is a very similar insight as what's behind VNN accelerators like the TPU or tensor cores with the GPUs. So we also employ vector chaining and design a functional unit to reduce memory bandwidth, a critical resource in FHE, but please see the paper for details. We run both deep and shallow benchmarks to measure CraterLake's performance. Deep benchmarks are those that require bootstrapping, so they include deep neural networks like LSTMs and ResNets, while shallow benchmarks do not require bootstrapping and are thus limited to 3 to 6 layer neural networks. This is the area breakdown for CraterLake, a total area of 472 millimeters squared. We implemented all the components of CraterLake in RTL and synthesized them with the commercial 1412 nanometer process. And for our experimental baselines, we use systems with similar area and power budgets, namely a 32-core server CPU and F1 Plus, which is a scaled up version of F1. So this table shows the execution time in milliseconds for CraterLake on both deep and shallow benchmarks, and also speedups versus CPU. So we see very robust speedups across FHE programs types from 2900 to 8600x. We also compare to F1 plus, and we see 11x gene speed up on these benchmarks, and up to 18x speed up. We also compare the shallow benchmarks at F1 plus, and we see much smaller speed up, so about 30% gene. And this really indicates that power accelerators, while they work well on shallow benchmarks, cannot handle deep FHE programs well. Okay, we also show here that the majority of energy is spent on compute in CraterLake, which is a great indication if you're specializing, right? And we get good utilization across our benchmarks. So to conclude, for widespread adoption of FHE, you really need to be able to accelerate FHE programs of any size, right? And CraterLake is the first accelerator that achieves this. And this means that CraterLake enables new exciting applications for FHE, like real-time DMN inference with neural networks such as ResNets or LSTMs. So thank you for your attention, and I welcome your questions.
Any questions from the crowd? Markel, Microsoft, Azure, and Wisconsin Areas. Very nice work. You presented mostly for deep neural networks. What is the limits of the class of computations that you can handle?
Okay, so great question. So there's sort of two things here. So if you remember, I mentioned scientists hold encrypted vectors, and that's a property of FHE, not of our accelerator. And that makes FHE particularly well suited to programs that work in batches or on large tensors. And that's why neural networks work well for FHE. But basically any program that has batches or works on tensors will be well suited to FHE. So basically, if it works well for FHE, it will work well on our accelerator.
Okay, so talking to your advisor, you can't handle data-dependent, clear text data-dependent branches, right?
Yeah, that would be hard with FHE. Yes.
One more question?
Yeah, so next up, Timmy from Prototype. So I have a question because you mentioned that your workflow is ResNet 20, right? There are some kind of like non-linear function inside ResNet workflow. So how can you have that kind of function in the CraterLake?
Yeah, that's a great question. Yeah, you're exactly right. So what you do to implement a ReLU, for example, is that you use a high degree polynomial approximation. And this isn't our contribution, other people have done this.
Okay, so how about the max pooling, this kind of stuff?
So max pooling, if you can do ReLU, you can imagine you can do max pooling. Basically, what you need to implement is a design function. And yeah, if you can do that, then you can do max pooling, you can do ReLU.
Thanks.
Yeah, thank you.
Thank you for the questions. We're short on time, so let's go to the next one. The next talk is the PS-ORAM efficient graph consequence support for Oblivious and the talk is given by Zhiru, who is an assistant professor of the Department of Bioscience at Illinois Institute of Technology. Her research involves designing secure and reliable memory architectures for future computing systems.
Sorry, I have to unmute myself. Yeah, now I'm unmuting myself. Okay. So hello, everyone. Thank you for joining today's talk. My name is Zhiru. I'm currently assistant professor at Illinois Tech. Today, I'm going to present our work, PS-ORAM, efficient crash consistent support for Oblivious RAM on NVM. So this work was primarily done by Mr. Liu Gang, my visiting PhD student from Hunan University, China. Okay. So here's the outline for today's talk, and I'll first start with the background. Okay. First, let's start with the target security vulnerability, which is called memory access pattern side channel leakage. So considering computing system with trusted processor and untrusted memory or storage, it is known to use encryption for confidentiality, using Merkle trees for integrity protection. However, even with all those approaches, it would still be very challenging to defend side channel attacks, such as memory access pattern side channel attacks in this example. In this case, an attacker may snoop and observe the communication bus between the memory and processor. And by observing these addresses, read and write intensities or frequencies, critical information may be inferred through this type of side channels. So here, I briefly mentioned a couple of recent classical and practical attacks by leveraging the memory access pattern side channel leakages. For example, a well-trained neural network architecture may be reversed engineering through it. In addition, a control flow graph of program may be constructed from it as well. Okay. So to defend the access pattern leakage, the Oblivious RAM was proposed as a general cryptographic solutions. So the ORAM is capable to obfuscate the memory accesses observed on the memory bus so that there will be no information leaked through this type of side channel. So the hardware version of ORAM can be implemented by adding the ORAM controller on chip, which sit in between the cache and the memory. So here we use a PS-ORAM, a classical and a simple ORAM protocol to show how the ORAM could work. The memory side is logically constructed into a tree structure, and memory blocks are stored on the tree bucket. While on the on-chip controller side, there is a position map and a stash used to enable the correct ORAM accesses. So there are 5 steps for one ORAM access. First, whenever there is a last level cache miss, we need to first check the stash to find out whether data is there or not. And if there's a hit, we can directly return the data from the stash to the processor, just like the cache. However, if it's a miss, then we'll need to go through with these steps and find out our data blocks from the memory. So in step 2, we need to go to the position map, which stores the mapping information of the data block to the pass ID stored in the main memory. So in this step, for example, we find out a block of interest is stored in the pass 2. And then at the same time, we're going to assign this data block a new pass ID so that next time you access this data block, it will not be in the same location as before. Okay. So with the pass ID known in the second step, in the third step, what we want to do is to load the entire pass of the data blocks from memory into the stash, decrypt it, and then find out the data block of interest. So if it's a write operation, then we can update this data block inside of the stash. And finally, in the fifth step, we're going to refill the pass 2 in this example by finding out the possible data blocks in the stash, and then complete one ORAM access. Okay. So by accessing more data blocks than the needed one, and also do the frequent remapping and reshuffle in the memory, ORAM is then capable to provide high security guarantee to defend memory access pattern leakage. So there has been many research advancing ORAM's performance on conventional DRAM-based system. However, when the back-end memory is changed from the DRAM, volatile DRAM, into the persistent non-volatile memory, there are many questions remain unanswered if there is a crash. So in general, persistent memory can work with on-chip persistent domain to enable atomic data persistence, which is good for the crash recovery. But ORAM complicates this situation in several folds. First, there is a mapping table in position map used to translate the block's address into pass ID, and such information is kept on chip in volatile state. And second, normal applications only have a few writes, while ORAM pass operations need to perform multiple writes operations like a transaction. So to enable a crash consistent ORAM system, we need to find out basically answer all the three questions here. Here first is that what are the cases for the data inconsistency, and second is how to enhance the system for the ORAM crash consistency, and also we need to minimize the architecture performance and architecture overhead as well as the performance overhead while securing the system. So we first try to apply existing crash consistent approaches to such a scenario. However, none of those solutions can work perfectly. For example, the traditional logging and copy on write will introduce a lot of memory space overhead for ORAM because it triggers much more write compared to the normal applications. Moreover, if we only selectively logging the change data, it may compromise the security. But hardware-based solutions, such as replacing all on-chip buffers into NVM, is indeed very slow. And there's a newer technology called extended ADR is not commonly seen for all types of processor, and also it is very expensive in terms of the energy and recovery time overhead. So if we go to the most common persistent memory or persistent domain choices, which is the ADR technology, we find that it cannot be directly to support the crash consistent ORAM either, but we could start from there. So next, we analyze the reasons that makes it challenging to design a crash consistent ORAM system. So with a non-volatile memory as a backend, everything written back to the memory is persistent. However, the on-chip buffers, such as data stored in the stash, is still in the volatile state. So if there's a crash happens at any stage of an ORAM access, the content, especially the ones that are modified in the stash, will be gone. So in the second case, in the second scenario is that it happens because in the second step, when we access the position map, we want to assign a new randomly passed ID to this access data block. However, this information is not persisted together with the target data block. So when there is a crash that happens after the step 2 of an ORAM access, to recover the state of ORAM system, we will not know if we should find the data from the old or the new pass ID. So there might be a mismatch between the pass ID associated with the data block and the pass ID retrieved from the position map. So third, if the system crashed during the write-back stage, it may just write partial data blocks back to the NVM, causing incomplete write, pass write, and overwritten data content in the non-volatile memory. And in this example, like data ECF are written back from the stash to the persistent memory. Then if the system crash, basically they just, these 3 data blocks will overwritten some useful information in the NVM, and it's not recoverable as well. Okay. So based on our crash analysis, we propose the PS-ORAM architecture. So this architecture incorporates the ORAM controller with the ADR type persistent memory controller, and the persistent domain include modified write pending queues and a drainer, which ensures that content entering the persistent domain will be written back to NVM without interruption. And additionally, we add a small buffer called temporary position map, which stores 30 position map entries that are not persisted yet. So next, we will introduce the PS-ORAM workflow. So in the first step, it remains the same. We first check the stash to find whether the data is there or not. And if we cannot find our data, then the next step is to access the position map. But now we modify the step a little bit by backing up the original pass ID into the temporary position map, so that we're not directly immediately written back this newly assigned pass ID to the persistent memory. So in step 3, it remains the same. We are able to load the full pass of the data blocks into the stash. And in the step 4, when we try to update the content in the stash, we also do not want to just directly modify the content there because that may cause data to be lost in the future. So whenever we try to modify the data in stash, we first we make a small copy in the stash and also modify the content to the new copied block. So the yellow block, which is the original data block, will still be written back to the original path. In this case, it will basically gain the automatically like data persistence when during the next eviction phase. So finally, the PS-ORAM write back and persist the data into the NVM, the 30 position map entries, and also the data blocks that needs to be written back to the NVM enters the persistent domain together, which ensures atomic metadata updates. So with the ADR support, the content in the write pending queues can be written back without interruption to the NVM. The position map entries could either be written to a secure region using recursive ORAM construction, or it could be written into and there are more discussions on the design choices in our paper. Okay. So to summarize, the PS-ORAM achieves low-cost data persistence without excessive additional writes, which greatly enhance the performance and NVM lifetime. PS-ORAM also supports atomic metadata write back so that the data mapping information is always coherent with the data block. Last but not the least, the PS-ORAM is secure with no relaxation on the thread model. It also does not introduce additional side channels. So we use the cycle accurate Gen 5 plus the NV main to simulate the system, and the workload includes several spec benchmarks plus our ORAM parameters listed in the tables on the right. So first, we show the overall performance of non-recursive PS-ORAM compared to a baseline ORAM system without the crash consistency support. And it only introduced about 4.29% overhead, while you can see the full NVM design, which represent the entire cache and on-chip buffers, as well as the main memory are using the normal time memory. These are going to introduce significantly higher overhead. So we also implement and evaluate the recursive ORAM design options, and recursive ORAM is intrinsically more expensive. Here, the first line, the baseline is represented non-recursive ORAM. So it is intrinsically more expensive, and by adding the crash consistency support, we only introduce 3.65% performance overhead. So the additional write traffic of PS-ORAM come from the persistent write operations for the 30 position map entries. As in this figure, compared to the ORAM baseline, the added writes are very minimal as well. So last, we compared the cost of PS-ORAM with more aggressive extended ADR design. Here we show two EADR designs, the EADR for the cache, entire cache hierarchy, and EADR for the cache plus the ORAM controller. So these are the two options that basically says that EADR needs to be extended to support all those buffer by providing the needed battery. So using the EADR to battery the whole on-chip components is much more expensive compared to the PS-ORAM, which it utilizes more conventional ADR type persistence domain options. Okay. So to summarize, in this work we perform crash analysis on ORAM built with persistent memory and identify that it's challenging to use existing solutions to build crash consistent ORAM. Our proposed PS-ORAM can achieve all the goals with moderate overhead and cheap atomic persistent protocols. The added performance overhead is also small in the non-recursive and recursive design. So that would be all, and I'll be happy to take questions, or you can also contact the first author if you have any questions. Thank you.
Thank you. Any questions?
Okay. What do you mean by environment? Sorry, I didn't get your question. Yes, yes, we can discuss it later.
So, okay, let's go to the next one. This is co-presented. The paper is There's Always a Bigger a clarifying analysis of machine learning assisted science attacks. It's going to be presented by Zhiru, who is currently a master's student at MIT, and he's also working at New York Times R&D, and he will be applying for the PhD program. So if you're looking for a next PhD student, this is your chance. And also, Zhiru is a fourth-year PhD student at MIT, who is advised by Srinivas and Weizhe. And his research interests lie in the introduction of trusted hardware, applied cryptography, and micro-textual science.
Thank you so much for the introduction. Hi, everyone. My name is Jack Cook. As Dimitrios said, I'm a master's student at MIT. I'm going to be presenting this alongside Zhiru, a graduate student also at MIT. And we're going to be presenting There's Always a Bigger Fish, a clarifying analysis of a machine learning assisted side channel attack. This work was also done with our other author, John Devadas, and our advisor, Manohar.
So guys, you're not saying this thing.
Oh,
we're not sharing.
my bad. Here, I got that. Yeah. Is it good now? Yes. Okay, great. So yeah, Jules is gonna start us off.
Cool. Yeah, thank you, Jacques. So nowadays, people use machine learning to mount very powerful side channel attacks. These attacks are great. They're highly effective and they even work in the presence of noise. But this talk is a cautionary tale. Indeed, these machine learning assisted attacks use machine learning as a black box, and they can find any correlation between an observed signal and a victim's secret. The problem with that is that these attacks are very hard to interpret. And the problem with the fact that they're hard to interpret is that if we don't really understand these attacks, developing effective defense mechanism can be very challenging. And so we think that this can only be addressed by doing better attack analysis. And today we'll present Bigger Fish, which is a detailed analysis of a misunderstood side channel attack. So this is the agenda. I will first go over some background, then I will walk through a surprising experiment, and then Jacques will take over to do an in-depth security analysis of the attack we're looking at today, and finally we'll conclude with some finding and a conclusion. So let me start with some background. Timing side channels. So the idea here is that if you have several orthogonal independent programs running on the same machine, they will end up sharing a lot of common resources. Think about things like a branch predictor, shared cache, or, oh, it's the wrong one. Okay. So yeah, you will have contention over these shared resources. So think about branch predictor, shared cache, or the DRAM controller. And so if there is contention over these resources, the activity of the blue program up there might have an influence on the timing of the red program. And now if the red program is malicious and controlled by an attacker, the attacker might observe the timing of its own operation very closely and try to infer a secret from the behavior of the blue program. In particular, it might collect some signal traces from its own execution, like the time it takes to perform a memory access, for instance, and then try to decode it. So here, decoding the signal means to find a correlation between the signal and the actual victim secret. And this is where machine learning can be especially handy because it's naturally very good at it. One example of an attack where the signal can be very complicated to analyze is website fingerprinting. And people are extensively using machine learning for this. So in this type of attack, website fingerprinting, the victim program here in blue is a web browser, and the attacker tries to guess which website the victim is currently visiting. So let me tell you more about why fingerprinting attacks are so powerful. So as I just said, the goal of website fingerprinting attacks is to leak sensitive information about a victim by spying on their web browsing activity. So these attacks are pretty bad because they're very dangerous because they can leak a lot of private information about the user. Think about all the websites you visited in the last 24 hours. It might tell a lot of information about you, like your religion or your political inclination. These attacks are pretty bad because they're also pretty easy to mount. Like an attacker program can be run directly in JavaScript by in a malicious page, open in another tab of your web browser, and that's very powerful because it only requires an attacker with very low privileges. And finally, this type of attack is perfect to exploit a side channel, and it's a very good fit for a machine learning-based decoder. Let me actually walk you through how machine learning classifier can be trained and used in this setup. So first, we have an offline phase or training phase, where the attacker is going to create a training set by collecting an important number of traces from a set of popular websites. So these traces are labeled with a corresponding website and used to train a machine learning classifier. Once the classifier has been trained, the online phase of the attack can be carried away. The attacker will collect a trace corresponding to the actual victim activity and ask the machine learning classifier to infer which one of the popular websites was visited by the victim. So this method is very robust and can make it possible to exploit very noisy and cryptic side channel signal that would be extremely difficult to analyze otherwise. So far I've told you how the machine learning classifier can use these traces. So now let me tell you how we collect these traces using side channels. So this is the specific existing attack we're going to analyze today. And it's a cache occupancy attack. So we've put the attacker codes on the left-hand side of the slide. And as you can see, the code is pretty simple. Let me describe it to you, I guess. So you have this outer loop that will basically constantly run. And inside of this loop, we'll first initialize a timer and then a counter. And then you have this second inner loop, this while loop, that will basically measure 5 milliseconds. And inside of this inner loop, the attacker will increment a counter and perform some cache sweeps. And so at a high level, what this code is doing is counting the number of time an attacker is able to sweep the entire cache every 5 milliseconds. So that's also why we call this attack sweep counting attack. So as a result, given this code, it's kind of easy to assume that the side channel exploited in this attack is the cache. And the intuition here is that one after the other, the victim will put some elements in the cache, and that will impact the timing of the cache sweep the attacker performs again and again. But now let's look at the surprising experiment. In this experiment, we'll keep the same attacker code, but we'll remove the cache accesses from the code. And so if we now look at what's left, it seems like we're only incrementing a counter and saving its value every 5 milliseconds. So at a high level, what this code is doing is profiling the instruction throughput of the attacker. So now if I ask you, what should the attack accuracy do? If we actually remove the memory accesses and we think that we're observing a cache side channel, well, the accuracy should drop, right? But that's where it becomes interesting. Here's a sample from our results. So this is the accuracy for an attacker to guess which website was visited by the victim out of a set list of 100 websites. You can see that our results are consistent over diverse configurations, and our attack performs better than the sweep counting cache occupancy one. For instance, for Chrome running on Windows here, the sweep counting attack has 80% accuracy, while our attack performs better with 93% accuracy. So given the surprising results, now we might ask ourselves the following questions. Which primary side channel are these two attacks actually exploiting? And so it's important to understand that this is kind of a challenging problem. The reason is that there's so many hardware resources shared between these two programs that really finding the primary source of leakage is kind of difficult. And we don't have specific techniques or method to answer this question. Okay, so far, I hope I've convinced you that machine learning assisted attacks are kind of hard to interpret. And in the rest of the presentation, Jack will show you how we've performed a detailed analysis of that attack and what is the root cause side channel that we've actually discovered.
Thanks, Jules. So at this point, we essentially have a machine learning assisted attack that's being powered by some unknown side channel. Now, we're going to analyze it to figure out what this unknown side channel really is. As Jules mentioned, this might be a difficult task because there may even be more than one source of leakage. For this analysis, we're going to return to the classics, the scientific method. We're going to modify our independent variables, run experiments, observe results, and report conclusions. Let's start with our first observation. We have 95.2% accuracy on this website fingerprinting task when memory accesses are removed from the attack. So we went back and did our research And we realized, as Jules said, that this attack is essentially measuring instruction throughput over time. So what could cause throughput to change? Our first hypothesis is actually frequency scaling. We have the CPU trade-off that's kind of, it's, a trade-off between increased performance and energy savings. And our idea was that when frequency scales up, the attacker is able to increase its counter higher. And when frequency scales down, it doesn't implement its function. That's what causes the side channel. So we run an experiment with frequency scaling disabled on our computer. We train a model and we get 94.2% accuracy. So our accuracy only went down by 1 percentage point. So our conclusion here is that little to no signal is coming from frequency scaling. So let's do this again. We have 94% accuracy. What else could cause it to change? Our next hypothesis was CPU core contention. Maybe when the attacker and the victim, they're both web browsers, they're pretty complicated processes. Maybe they're doing stuff on the same CPU core, they're contending over the same resources, and that's what is causing the side channel. So we repeat this experiment with the attacker and the victim pinned to separate cores. This time we got 94.0% accuracy, a decrease of 0.2%. So clearly, there's little to no signal from CPU core contention. One more time, 94% accuracy. What else could cause it to change? Interference from system interrupts. This might not be intuitive at first, so let's talk about why we reached this hypothesis. System interrupts are used on every computer to deal with asynchronous events, oftentimes from hardware devices. For example, your computer uses graphics interrupts to render content on the display. Basically, what we thought was happening was when the victim process was loading this website, it was triggering a bunch of interrupts, to download network content, to display stuff on the page, to schedule, browsers like scheduling all that stuff. And then these interrupts are ultimately processed on the attacker's core. And so in the white region here, the attacker is in user space and it's executing its own code. It's implementing its counter over and over and over again. And then when we reach the orange region, the interrupt handler is run basically, and we're in kernel space now. And because the core is processing that interrupt, the attacker can no longer implement its counter. It essentially loses all of that time. And so we thought that this was what's causing the side channel. Crucially, and I'll get into this in a second, only some of these can be pinned to specific cores. Some of them can't. So we're going to run this experiment, and we're essentially going to run this experiment with all of the movable interrupts diverted from the attacker's core. When we ran this experiment, we got 88% accuracy, which is a decrease of 6%. So there might be some signal here, but there's still a lot left. 9 times out of 10, the attacker is essentially able to guess exactly which website you're visiting. So there's still a lot of signal. So let's talk more about this distinction between movable and non-movable interrupts. Here we have the proc interrupts file, which you can open up on basically any Linux computer. At the top here, we have all of your movable interrupts. Each row is a different interrupt, and each of the columns that are numbered, we have CPU 1 through 4, 0 through 3. That's the number of times that type of interrupt was executed on that core since the computer started up. A lot of these are very recognizable. For example, on this row, we have interrupts from your mouse. Every time you move your mouse, an interrupt is sent to process that event. We have interrupts from your keyboard, your network card to process, to download, upload data, whatever. SATA interrupts for your hard drive, graphics card interrupts to display content on the screen, and all that stuff. We also have a bunch of non-movable interrupts, and you'll notice that for each of these, the numbers are pretty high on all 4 cores. And this is because this is just how your operating system is designed. These interrupts cannot be pinned to separate cores. Some of these are a bit harder to recognize, but we can still see what they're doing. For example, timer interrupts are used to schedule processes between your different cores on your computer. And IRQ work interrupts are used when there's like a very long running task and your kernel can do a little bit of work right now, but it uses an IRQ work interrupt to schedule most of that work for later. So yeah, basically to summarize, these non-movable interrupts are, they're present on every computer. They can't be isolated from any cores. So your attacker is necessarily going to, it's going to hit some of these, and I'll explain that more in a second. They're necessary for the operating system to function, they can't be user disabled, and they have not been studied in detail for side channels. So let's go back to this scientific method diagram. We have now 88.2% accuracy with all of the isolation mechanisms that we've applied so far. Frequency scaling, pinning to different cores, diverting all the interrupts. So what else could cause it? Non-movable interrupts. So we want to repeat this experiment with the non-movable interrupts diverted from the attacker. But the problem is that this experiment is impossible. As I just explained, it doesn't matter which core your attacker is on. Some of the non-movable interrupts are going to execute on the attacker's core. So to take this analysis a bit further, we're going to use eBPF, which is a tool that allows instrumentation of the Linux kernel at runtime. We use eBPF to develop a tool that can monitor characteristics of interrupts. We essentially, it probes, or we inserted probes that basically record the time at the start and end of each interrupt handler. And we can then correspond this with the timestamps measured by the attacker to see whether those attacker gaps correspond with interrupt handler times. So here are some examples. This is a lot on this slide, but let's go through it. So the blue line is the counter values that are recorded by the attacker that Jules was explaining earlier. So at each, as time increases from left to right, these are the counter values that the attacker is recording. The black line is the time that your processor spent handling interrupts at that moment in time. And you'll see that when interrupt handling time increases, the counter value decreases. And this is because, as I mentioned, the attacker essentially just has less time to process stuff. And we can even notice a couple of spikes here. So for example, when Amazon.com, when we're loading Amazon.com, we have these like drops in counter value at 5 and 10 seconds after you started loading the page. And they correspond with huge spikes in the time that's spent processing interrupts. You can see it there again. When we're loading weather.com, there's like this huge like valley in the counter value distribution, and it's like a mountain in the interrupt handling time. We can even flip them, and you'll see that they actually correspond very well. The blue and black lines mirror each other pretty well. We can even do it one more time just for added effect. We additionally verified with this eBPF tool that 99% of these gaps that the attacker process is monitoring can be explained by the presence of interrupts. We essentially verified using eBPF, using those probes that record the time at the beginning and end of interrupt handlers, that these gaps are explained by interrupts, which really confirms our hypothesis. So there's plenty more in the paper. We have a really interesting randomized timer countermeasure due to the limitations of the browser environment that defeats our attack for the most part. We ran some experiments with virtual machine isolation where the victim and the attacker are in separate virtual machines and saw what that did. We have further discussion of these non-movable interrupts and their security properties and so much more. We also have an interactive demo that you can try out. Let's see it happening here. So here we're going to collect a 5-second trace on Amazon.com where the attacker process in the background is collecting traces, and on the, you can see we're loading Amazon on the page. I sped it up. We're going to record 3 more traces on weather.com. It's set up, so you can just see it load 3 times. And then here we have the traces. You can even see visually that these traces are very different from each other. And when you train a model on this, of course, this is why we get such great accuracy. Machine learning is just really good at figuring out what the label is of these traces, given a lot of training data. So to wrap up, our findings and conclusion, machine learning assisted attacks are very powerful, but they can be tough to interpret. This sweep counting cache occupancy attack primarily exploited system interrupts, but because of the black box nature of their machine learning model, it seemed like they were exploiting the cache side channel. Non-movable interrupts have very strong security indications that need to be further studied, and we've released our analysis toolset on GitHub. So I encourage all of you to try out that demo from the video. There's a QR code, and you can just go to that link as well. And this really shows that, you know, in the attack that we've analyzed, researchers thought that the primary side channel being exploited was the cache. Our work shows that interrupt side channels are in fact the bigger fish. Thank you, everyone.
Any questions from the yes, what are we going to do with us?
Sorry?
What are we going to do with us?
I don't know.
I don't know either.
Yeah, I'm not sure.
I think you need to like support within your architecture of these more adversarial like how these things are spread out.
Hi, nice talk. So I have a question for you. talking about the scientific method, right? You control for one factor at a time, and you fix that factor, and there's little change in accuracy, say that this factor doesn't contribute much. But how can you be sure that the factors are additive? But what if there are like other influences such as you put this factor this group of
Yeah, so that's a good question. We really tried our best in each of these experiments to only modify one thing at a time. And then in our paper, we explained our methodology where we were generally running like 10 experiments or something, and we took the average of these. We did some t-tests to determine significance of these, single factor at a time. And so we're pretty confident that it's due to those individual things. But there's more info in our paper.
Thanks.
More question?
Okay, thanks for the talk. I was wondering that the cat frequency attacks are kind of slow. So have you also looked at some faster attacks? And because this is basically we are trying to figure out why these error bars these attacks occur. And when you look at some faster attacks and you have some insights on what might be the cause of the error bars in those attacks.
So just to clarify, when you say slow, you mean because you need to load it for 15 seconds?
For example, if you like see things that might be at a scale of weeks, whereas if you do like AES, 810 or AES, AES private key extraction, it might take 1,000 seconds. So it's much faster, but there are some system level parameters that kind of change that.
Yeah, so I think there are certain things that for this paper, we really focus on the limitations of JavaScript and in browser, where precision of the timer does not go beyond 0.1 milliseconds per row. So that makes that kind of attack impossible. So this paper, the types of attacks that this work is really good for are things like fingerprinting, where there's a very clear trace over a longer duration of time, maybe at least 1 second. But there's more that you can do with non-JavaScript environments as well.
Yeah, I think we said the country felt I had no idea that just means great concepts like critical level and true, but it's other effects beyond what the scientific being as saying like maybe it's just structure different models.
More to come.